Hey guys, I hope you had a happy Easter. So today we're going to start 6.5. We're not going to finish it today, we'll finish it tomorrow. And we're going to talk about what the characteristics of tangent and cotangent are. So I think we wrote in tangent on your unit circle, but if you didn't, go ahead and pause the video here and fill these in like kind of off to the side, because it doesn't actually, right, tangent isn't actually a point on the graph of the unit circle, but it is related to the graph of a unit circle, right? Because tangent is sine over cosine. So that's how we get these numbers. So like if I'm talking about 0, the reason why tangent of 0 is because this point right here is 1, 0, right? It's, wow, that looks bad, I'm sorry. This point would be 1, 0. So this would be 0 over 1 would equal tangent, which is just 0. Okay, right here it would be the square root of 3 over 2 over the square root of 1 over 2, right? So it'd be the square root of 3 over the square root of 1 half, which gives us the square root of 3 over 3. Right? And then because sine and cosine are the same at 45 degrees, they're both the square root of 2 over 2. That's why the tangent of 45 is 1. Because something divided by itself is just 1. Okay, so that's where these numbers come from. You're just dividing sine by cosine. So you're taking the y value and you're dividing it by the x value. Because you have a fraction over a fraction, you have to flip and multiply, and that's why some of these look a little different. Okay, now the ones that aren't labeled are the ones we really need to talk about here. It's 90 degrees and 270 degrees, right? Now, if I'm on the unit circle, you should have these values here. You should have 0, 1 on your unit circle, and here you should have 0, -1. Now, if I'm saying that sine is the y value, for tangent at 90 degrees, I would get 1 over 0. Now, most of you see it right now. The reason why we don't have a value there is because if I'm dividing by 0, I don't actually have a value for tangent. So this is undefined. It doesn't actually happen here. Okay, so same thing with this 270. The tangent of 270 is -1 over 0, and because I can't divide by 0, I get undefined. So if you would type in tangent 90 into a graphing calculator, it would say domain error, right? Because it's telling you I can't do 90 because I can't divide by 0. Okay? So when we're graphing these, we have to think about that on the graph as well. So what I did here for this next slide is I took that table and put all of those tangent values into my table so it would be easier for me to graph. Now, personally, when I'm graphing, I think the easiest things to graph are my asymptotes, because I know at negative pi over 2, I have an asymptote. It's never going to touch it. It can't, because there's a domain error there. Okay, same thing goes for the domain error here at pi over 2. And then if I'm looking at my chart, I think I have another one at 3 pi over 2. Okay, so first thing I do is fill in my asymptotes. The next easiest thing to do is that all of your pi's is to put a 0. So at 0, I get 0. At pi, I get 0, right? I would get 0 every other time like that. Okay, I'm only going to graph 2 periods of tangent here, and that's why it's like that. Okay, I'm going to scroll this down so we can see it a little better. Okay, now I'm going to fill in the rest of it. Now, these like square root of 3s, those are kind of hard to graph. And like the square root of 3 over 3, I don't actually know what that number is off the top of my head. But I do know something about asymptotes and lines. So anytime I have a graph, a line is going to approach the asymptote. So it's going to get as close as it can to it. And as it gets closer to it. So the ones I'm going to graph that I know for sure are the pi over 4s, because I know pi over 4, regular pi over 4 is 1, and I know negative pi over 4 is -1. So if this is what the graph looks like, and I know it's going to approach the asymptote, all I have to do, let's go like this. And that's what tangent looks like. It is periodic. It happens over and over again, just like sine and cosine. But it does have a few different characteristics, okay? So now, this is tangent. If I was going to graph cotangent, the only thing that would change, really, it's just the reciprocal of this. So what I would do is I would change all of these numbers. Anytime there was a 0, there would be an asymptote. Anytime there was an asymptote, there would be a 0, and then it would go the other way. It would be kind of like be a flip across the axis. And I'll show you what that looks like in just a little bit. But before I go into that, I do want to talk about these characteristics. So now on this graph, if we're talking about amplitude, we're talking about its maximum value. Now, if you notice on this graph, we don't have a maximum value because the arrow shows us that we're going up forever and ever, right? Same thing with this down arrow. It means we're going down forever and ever. We're getting as close to that asymptote as we can. So there is actually no amplitudes for tangent and cotangent. And its period is a little different too, because it does have an asymptote. It's bound by a certain amount of time. So if I'm going to look at this, I'm going to say, okay, well, it goes pi over 2 that way and pi over 2 that way. So a full period for tangent is just pi. Okay? Kind of makes sense. It's created by the 2 functions. So if I divide 2 by 2, I would get 1. Right? 2 pi by 2 pi, I'd get 1. So that's why it's just pi. But it does still follow those transformation rules. So now I'm going to flip to that characteristics. Go ahead and pause it if you would like. These are the characteristics of tangent and cotangent. So the domain of tangent is all real numbers except odd multiplicities of pi over 2. So that means like that negative pi over 2, pi over 2, 3 pi over 2, 5 pi over 2. Those don't actually work. That's where you have your asymptotes. Okay. The domain for cotangent, again, is just a little different. It would be where all of the zeros are on tangent. So that actually happens at pi's. So pi, 2 pi, 3 pi. Those would be your asymptotes for cotangent. Now the range is all real numbers. So since we have a range that goes from infinity to negative infinity, we don't have an amplitude. But the period for each is pi. Now the x-intercepts change because we are talking about 2 different functions. Just like sine and cosine, they just move 1/2 pi off from each other. Same thing with tangent and cotangent. Okay, so every time you have an x-intercept on tangent is where you have an asymptote on cotangent. And every time you have an asymptote, x-intercept on cotangent, you get an asymptote on tangent. All right, so now the big things to talk about here with transformations is this. So since there's no amplitude, the a value goes back to its original, and that's just a vertical stretch or shrink. Right? So if it's 2, it's going to stretch it out. It's going to get closer to those asymptotes, a little less fast because it's trying to go higher faster. Okay, and if it's less than, it's going to get really wide, right? I'd go ahead and play with it on Desmos if you wanted to see how different graphs look, okay? The period for each function is pi over b. So just like before, we said, well, a full circle is 2 pi for sine and cosine. and we would divide that by the b value. Because the period of tangent and cotangent is pi, we just have to divide it by that b value. Okay, so then it does give an equation for your vertical asymptotes as well. And it's saying all you have to do really is divide the period by 2 for tangent, or just give the period for the vertical asymptote on cotangent. Okay, so if I'm going to graph this function, 2 tangent 3x, what I'm going to do is I'm going to say, well, this 2 is a vertical stretch. So I know it's kind of like that Laffy Taffy. It's going to go up really, really fast. And this 3 changes the period. So the period of this function is pi over 3. Okay, so what this is saying is it's going really, really fast. Okay, instead of going halfway around the circle, like all the way around a circle in 1 pi, it's saying it's literally happening 3 times in 1 pi. Okay, so if I were to graph this, I'd make my graph, and I'd say, okay, well, pi over 3 is a full period. I didn't move left or right, up or down any, so I know that my x asymptotes, the first one is at 0, and I know and instead of going over to pi over 4 and up 1, I'd say, well, if I go 1 notch, it should go up 3, because of, well, not 3, it should go up 2, because of this vertical stretch of 2. Okay, so if I go 1 notch over here, it should be at -2, because that 1 notch. Okay, if I go 2 notches over on each side, that's where my period should be. I'm going to say this is pi over 6, and this is pi over 6 negative. Now, some of you are wondering why I did pi over 6 instead of pi over 3. It's because I want this whole area from this dotted line to this dotted line to be pi over 3. So I need to go half of pi over 3 this way and half of pi over 3 this way. And that's why I said those asymptotes were at pi over 6. Okay? And after I have those in, all I'm going to do is connect the dots and approach the asymptotes. So it's going to get really skinny like that. Okay? And if I wanted to do another one, that's what I would do. So it's still 4 notches. It's like, if you're talking about graphing it, 4 lines is still really what you're talking about. But because we're going on both sides of it, we get half of each pi, half of each period. So pi over 3 means pi over 6 on both sides, right? So that's kind of what this was talking about for that vertical asymptotes of tangent. Again, if you want to write that down, go ahead and pause the video. All right, cotangent, a little different, right? It's just that reciprocal function, so it has a little different properties. Still follows the same rules, though. Okay, so I'm looking at this, I'm saying, well, it's not a vertical stretch or anything, so if I go over 1 notch, I should go up 1 notch. Okay, and this 1/2 means I'm saying pi over 1/2 is the period. So 2 pi is actually the period. Now, because this is the reciprocal function, I know anytime it was 0 before, it's going to be an asymptote. So I need to have 1, 2, 3, 4 notches in a dotted line. And on my 4th notch, I'm going to say that's pi over 2. This actually, I think tangent and cotangents are easier, because now that I have that, I can say, well, I know it's got to be 0 in the middle. And because it's a reciprocal function, it's just going to flip. So if I'm talking about cotangent, it's going to look like this. So if I go over 1, I should go up 1. And if I go over 1 this way, I should go down 1. Wow, my line doesn't look very nice. So this is what cotangent would look like. So it just goes the opposite direction. So a way to really tell if something is cotangent or tangent is the direction that it goes. So if we look at number 5, we see that it's going this way. It goes up on the right side and down on the left. Cotangent goes up on the left and down on the right. So that should help when you're doing these graphing sine and cosine and matching, or graphing tangent and cotangent and matching with each one. Okay, now if it doesn't have a vertical shift, tangent should have a spot at 0, 0. Cotangent would have to have an asymptote at 0, 0. So that's kind of another giveaway, right? Now the problem with that is if we do put a parentheses, if I would change this to 1/2 cotangent, I'm sorry, I shouldn't put a parenthesis there. Just erase all of that. If I changed this to 1/2 cotangent x plus 3, now this plus 3 would move those asymptotes because it would be moving it left or right. So if we have a plus in the thing, you need to really look at just which direction is it going. Is it going up on the left or is it going up on the right? And that'll give it away. Okay, so I hope that was helpful. If you have any questions, please let me know. What we're going to do for our assignments, we're going to do page 506. We're going to do numbers 2, 3, and I picked a few of the tangent and cotangent problems from 7 through 28, okay? So now the directions are a little different. We're not going to actually end up graphing them on paper. I have a matching where you'll have to match the graph to the function. So I think the easiest way for you guys to do this would be to check them with your graphing calculator. Again, make sure your graphing calculators are in radians. Or if you want to do it on Desmos, that's where I made the pictures from. So if you type it into Desmos and find which picture looks like the one that I have, that should help too. But again, if you have any questions, let me know. Have a nice day.